Okay, so as we get started, we'll just, let's say, rehash or go over what we did this morning. And I just asked for volunteers, and students had said, well, I'll do some organic compounds. Another student said, well, I'll do some naming compounds. And then we reviewed another one of these, and that's what we did in the morning session. So what we had done is, and we didn't record this morning, but this is exactly what we had done. We have a C7H16 compound known as heptane. So what had transpired is we said, well, let's draw 4 isomers of heptane. And there might be more, but I think that's pretty accurate. Because I think it's isomers that students tend to struggle with the most. So when we do this, we have to have a compound that looks like this. It would still have this and this, but it's not going to be a straight chain like this, okay? And also what students tend to do is maybe they'll go like this and say, oops, is that an isomer? It's got C7H16. Nope, nope. Because we're thinking this is an ethyl group. That would be, but it can't be here. That's the issue. So when this is all written out in blue, what would you call that? Heptane. What do you think you might call this?
Like just ethyl pentane?
Nope, there's no derivatives on here.
So would that also be heptane?
This is still heptane because this is all one continual chain. It's just bent. So we would still have heptane when we look at that. So let's go back to.
It has to be on the front in order for it to be an isomer.
It can be in the middle. It can be an isomer. You have to put it in the middle. So what they had discovered is what's the simplest thing that you can do to make an isomer from heptane? Okay, so when we perceive that, okay, is that an isomer?
No.
So sometimes what happens, what would you get if you named that compound?
You get hexane?
Yeah, it's a hexane compound. And is there anything branching off of that hexane?
Methyl group?
Yeah, there's and on which carbon is that methyl group? Yeah, so you have 3-methylhexane. You still have 7 carbons and 16 hydrogens, but the structure is different. Okay, then these only get tougher as you go. This one was, for methyl groups, it was maybe mildly tough. So what else could we do to create or I should say, an isomer? You can go at the second carbon, which is either here or here. So we'll put it down there. Now we have 2-methylhexane rather than 3-methyl when it was under here. Okay, so we'll go ahead and erase that. Okay, and now we're back to heptane again. 5, 6, okay. All right. So then I was probably one short on here. I had it in my mind that it was 3-methylhexane and 2-methylhexane. Okay, so now we're back to heptane. All right. So can we put more than one derivative on the same carbon? Yes, you can. So we're going to take these 2 back off again. Okay. So we have to place 2 more carbons somewhere, which we know we can't put here. We established that. That's part of the parent chain. So when you say 2 and 3, all right, there's 2, there's 3. And let's stretch this one out maybe a little more. Okay, so then it doesn't look like these carbons are bonded to one another. So now, and remember, if you name these, then you might not double back or put 2 of the same compounds down. So when we name this, what do we have? Nope, not heptane.
Dimethyl
How many carbons are in this chain?
pentane.
Yeah, so you have 2, 3 dimethyl pentane. Okay,
So would that still be an isomer of heptane or no?
that is an isomer. Yep. So let's chop this one off of here. So can we do that? It's a trick question. The answer is no. Then you have the same compound again. You still have 2, 3 dimethylheptane. We just did. Other side of 3 on this one here. Okay, so 1, 2, 3. So the other side of 3, are you talking about this one?
No, the top.
The top.
That's 4.
Okay, so the other, okay. So because I kept hearing the other side of 3 thinking this way. You're talking about other side this way. Yes, so you could do that. That is an isomer. So you have what now? 3, 3 dimethylpentane. Okay, and then that would be close to being it. There's one more you could do with 2 methyl groups. Since these are on the 3rd carbon, where else could you move them? Well, if you move it over here to what you think is the 4th, it would no longer, it wouldn't be 4, it would actually be 2. This is an isomer. Now we're just going back the other way. 1, 2, 3, 4, and 5. So 2, 2 dimethylpentane, 3, 3 dimethylpentane. Now probably the most difficult one to do. Put a, or I should say, an ethyl group on here. Okay. So what first might come to mind? Okay, so there's 5. We might think 2 carbons. That's an ethyl group, right? So do we have an ethyl group branching off of that carbon? It's a trick question. No, we don't. Because, again, the first rule to do is find the longest continuous chain, which we have 5 going this way, right? But if we do this, 1, 2, 3, 4, 5, 6. Now we've got 6. So what this is saying is we have 3 methylhexane. And we've done that one already. That's what makes this so difficult. Okay? So, yes, we would agree that C2H5 is an ethyl group. It's just that it's in the wrong spot. So, which direction would we possibly move this to then? If we go 1 to the right. And remember, we can't go 1 to the left. Then we're back to heptane again. But if we go 1 to the right, now what would we have? We do have an ethyl group now. And it's on which carbon? Okay? So in this case, it does not matter which direction you go. There's 4 different ways you can go. You could say 1, 2, 3, 4, 5, and then here's an ethyl group. You might think, well, what about if we went 1, 2, 3, 4, 5? Well, same thing. It's just the ethyl group is branching this way instead of down. What about if you go this way? Well, then the ethyl group is going over here. And what we're saying is you can go this way, you can go that way, you can go this way, or you can go that way. All 4 of them result in the same compound. So what would we name that? So it's got to be pentane. What type of pentane? Nope, not methyl. And on which carbon is that ethyl group? Yeah, so we got 3 ethyl pentane. So that's what makes isomers maybe so difficult to do. So that's what we did in the morning session. Then the next part, okay, what we had done was this follows. We put two compounds up on the board, and we had a student come up here and name them. So we did this, or write the formula, excuse me. This was one. Then the other one was this. Okay? So we need to write the formula out for these. What is the symbol for sodium? Okay? What's the symbol for sulfide? Sulfide. That would be sulfite. I mean, you might need your periodic table. Maybe, maybe not. I don't know. You might. Then that's sulfus.
SO?
That's sulfate.
Yeah, and SO4 is sulfur.
Then that's persulfus, I believe. SO. Now, the SO2 is sulfur dioxide. And SO would be sulfur monoxide.
SO, wait, is there more sulfurs or more?
See, you're making this more, and that's how we learn.
Or is it just sulfur?
It's just sulfur.
Oh.
Okay? Go by your negative ions. What charge does sulfur have? Because, well, what column is it in the periodic table? Column what?
6.
So that must mean it has a charge of negative what? No. How many more electrons does it want to become stable?
Sorry, -2.
Yeah, because it wants 2 more electrons. This is -2. Sodium is an alkali metal in column 1. So it is plus what?
Plus 1.
Those charges don't add up to 0.
So you need 2 sodiums.
Okay, so your least common multiple is 2. 2 divided by 2 gives you 1. That's what we've got. 2 divided by 1 gives you 2. So that answer tells you need to put that below. Then maybe the last thing you'd have to do is, okay, sulfur has an atomic mass of 32. This has, it's a little more. We're just rounding these off to the nearest whole number. Sodium has an atomic mass of 23. How many of them do we have?
2.
So that gives you 46 plus 32, which would give you what, 978? I think so. So approximately 78 grams per mole, or just 78 atomic mass units, however you want to label that. So this one's maybe a little more difficult. What is the symbol for iron? Okay, now this is a polyatomic ion. What is the symbol for hydroxide?
OH.
Okay. What is the charge of our hydroxide?
-1.
Okay. And what is the charge of our iron? Okay, and it can have multiple charges, but we don't have to guess because it's written here. So this is plus 3. What's your least common multiple? Okay, so what's 3 divided by 3?
1.
And we've got 1. What's 3 divided by 1?
3.
Okay, we just need to make one slight little change.
You gotta put parentheses around.
Okay, and then once we put parentheses around there, then we have it. Okay, so if we had to add these up, this is approximately 55. Oxygen is what?
16.
And how many of them do we have? So that would give you 48. And then hydrogen's approximately what?
1.
Okay, and we've got 3 of them. So 3 plus 48 gives you 51. Plus 55 is what, 106? I believe that's what the atomic mass of this would be, 106.
So for the semester test, we're gonna have to do the atomic masses, right?
Maybe just one compound, not all of them, because otherwise we'll run out of time.
Just write the number and circle it or something.
Just circle it. And what you're asking is, like I said, 55 approximately for the iron, 16 times 3 for every oxygen gives you 48, and then 3, and then adding those together. Okay, 11 and 5 gives you 6. Okay, so, oops, 106, not 96. 106. All right. Questions on this? Okay. Go ahead and erase this. Then the last thing we did was they had chose bismuth. Okay, so what is everything that you can tell me about bismuth when you look at it on the periodic table?
Oh, are we doing like a Bohr model?
Bohr model, yep.
Element 83.
Okay, so why is that 83 important?
Because that's the number of protons.
Okay, so we have 83 protons, and if it's neutral, we'd have 83 electrons rotating around this nucleus. Okay, so if we follow our slide rule and we put these electrons in the proper energy levels, that's why we use the slide rule. Okay, so how would we start this? We know, okay, so 1s2, then what?
3p6, 4s2, 3p6, 4p6, 5s2.
We're going to put a number here. We left off with 5p6. Oh, I was off when I'm trying to visualize it in my head. Now we're going to go down to here. 4d10. There we go.
6s2.
Now this gets to be a little tricky because if an element is this big, we know we're going to have to go through the F block. Okay? So we just did 6s2. What comes after 6s2? It's probably right here. 14. Okay. Now we can go back up to here. And then that's, okay, so let's stop for a moment. Let's see once where we're at. Because this is how you can use that periodic table. Use it as a tool for you. Okay? Because when we locate bismuth, okay, what period is bismuth in? Well, the periods are over here. I don't think it's 5. 1, 2, 3, 4, 5, 6, and go across. Right there it is. So that must mean we need how many energy levels then? 1, 2, 3, 4, 5, 6. So that checks that box. Then what block is bismuth in? Not the D block, the P block. Okay, so then what column in the P block only is bismuth in? No. No. The P block only. Right, because that's where your 3 comes from. You said that we needed 3 more. Then what we did is we put a box around it. So 6th period, that's where the 6 energy levels come from. It's in the 3rd column of the P block. That's where the 3 comes from. Then for the entire period, it's in column 5. And that's what happens when you add those 2 together. And you can always check your answers here because, so we count the number of 2s. We got 1, 2, 3, 4, 5, 6. 6 times 2. Okay. Then let's knock our 6's out. 1, 2, 3, 4. 4 times 6 is 24 plus 10, 34, 44, 54. Okay? And then we just have 14 and 3 gives you what? 14 and 3 gives you 17. So then what is 2 plus 4?
Six,
Plus 7 more?
11, wait,
Not 11.
13.
13. Okay? So then we carry that 1. That gives us 2. 5 more. No, I goofed. Okay. So 13, 1. That gives you 2. 7. 7 plus 1 more gives you, these numbers match. So that's got to be right then. Okay. So then the last thing we did was an electron configuration. So, who would rather do the shortcut?
I can do a shortcut.
Okay? Because if not, otherwise, you write all these out, all these numbers sitting next to one another, it's going to go all the way across the board, depending how big your handwriting is. But if we wanted to take a shortcut, which we can do, okay, which noble gas would we use for that? We can.
We would use xenon.
Xenon, because notice we can't do this one because that's too big. This has an atomic number of 86, so that's over, or 83, so that's too big. So that must mean we got to go down one more column or one more row, which is xenon then. What's the atomic number? Okay. So what period is xenon in? That's the block. We want the period. The 5th period. What block is xenon in? Okay. And then finally, what column in the P block is xenon in? So that must mean the 5th period, the P block, and the 6th column, those are all filled up. So then what comes after 5p6? Okay? Notice we're just going to do a linear depiction of all of those electrons. What comes after 6s2? 4f14.
5d. 10.
Okay? And then we just have one more number to put down. 6, someone said it, 6p3. And we can check our answers here too. 3 plus 10.
3 plus 10,
13 plus 14 more is 20, 27, plus 2 more, 29. So we got 54 and 29. 4 and 9 gives you 13, so 6 and 2 gives you 8. There again, your numbers match, so that's got to be correct. That is what we did in the morning session. That's all the further that we got. Okay? So that's all I have. We'll continue to do this reviewing tomorrow, and I believe something to think about is I have it listed as exam being on Thursday, but that probably will not work because we track leaving for White on that date at 11:40 is what it's scheduled to be. So chances are we'll just push that back to Friday then instead. Okay. Front row. We're good. Back row. All right. That's all I have. We'll catch up to you next time.